available on our website to view after the meeting. And also just a reminder that you can always visit our website to stay up to date with anything SEI Philly going on at sei-philly.org. And you can always shoot us an email too at phillysei@gmail.com. So quick introduction of our current board. As I said, my name is Nikki Eno. I'm currently serving as the SEI Philly chair. Keith Merle is serving as our vice chair. Keith Urban. Mike Urban. That's the first time that's ever happened. Mike Urban. The problem is you have Keith Merle next to Mike Urban. So put it together, you have Keith Urban. Mike Urban as our treasurer. Colin Drager as our secretary, Greg Dunn as our program director, William Kittleman as our director of public relations, and Alex Domino as our deputy director of public relations. And also want to acknowledge our past chair, Jack Cardinal. So we recently just held our annual golf outing on May 3rd, which was a great success. So thank you to all that came out and sponsored the event.
After the tone. When you have finished, please hang up or press the pound key for more options.
Just a reminder, anybody on the call not speaking, please mute yourself. So again, thank you all to the sponsors and everybody that came out for our 2024 golf outing. The purpose of our golf outing is to financially support our student scholarship that we give out every year. And we want to acknowledge our sponsors from last year's golf outing. Our top sponsor was AECOM, which our scholarship was named after AECOM this year. And then in addition, prize sponsors. So thank you to all. So welcome everybody to our May 16th lunchtime webinar. Just a reminder again, please mute yourself if you're not speaking. Any questions that anybody has during the presentation can be addressed at the end by using the chat function, or you can just go off mute and ask the question. In addition, any follow-up comments or questions can also be sent to our SEI Philly Gmail address. So today's topic, we have UBC Tallwood House at Brock Commons, which talks about achieving new heights with mass timber construction. Anybody on the call today will receive a PDH for attending today's meeting, and the link to the PDH will be shared in the chat at the end of the meeting. So today's presenter, we have Eric Vaughn. He is a project manager at Fasten Ep. He received a Bachelor of Science in Civil Engineering from Columbia University and a Master of Science in Structural Engineering from the University of California, San Diego. Prior to joining Fasten Ep in 2021, Eric worked at Thornton Tomasetti in New York City. Eric is a licensed professional engineer in New York. His experience at Fasten Ep includes project management for a variety of commercial buildings, conference centers, office buildings, as well as high-end custom homes. So with that, I will pass it over to Eric to start his presentation. Thank you.
Thanks, Nikki. Hello, everyone. And Nikki, can you give me presenter privileges, please?
Sorry, I thought
no worries.
I had already done that. My mistake.
No worries.
Just gonna find you.
There we go.
Should be good.
Yep. Whoops, wrong screen. All right. Hello, everyone. Thanks for coming. My name is Eric Bone. I'm a project manager at Fasten Ep. And today I'll be talking about Tallwood House at Brock Commons, which is at University of British Columbia in Vancouver. This was built in 2017, and at the time, this was the tallest mass timber building constructed. Oh, whoops, I should hide. So here's a quick agenda. I'll start with an overview of our company and then dive right into the project, followed by ending with the talking about our concept lab, which is our internal research and development arm in our company. So who we are. Fastenet. We are structural engineers. I'm in the New York office. We have offices headquartered in Vancouver, Seattle, and Toronto, with 2 offices in Germany. We work with all materials in all sectors, but our expertise comes in timber and hybrid structures. Here's quick bullet points of our specializations, and I will talk into highlighting these 4 highlighted ones in red at the UBC Tallwood project. Now to get into the project background. So this is an 18-story student housing at University of British Columbia, Vancouver. It's 175 feet tall. It's 17 floors of 2-way point-supported 5-ply CLT. And at the time, this was the largest application of point-supported CLT on a project in the world. It has a steel roof, all coming down on a concrete podium, transferring out on level 2. And the lateral system is 2 full-height concrete cores. And this was built in 2017, so before I joined Fastenet, but this has been a template landmark project at our company for future point-supported CLT projects that we've worked on. A little quick mass timber refresher. This might be new to some people. It might be they already know this, but cross-laminated timber on the left, the solid engineered wood panel consisting of several alternating layers of dried lumber boards bonded with adhesives to form a solid
You've
panel.
reached the maximum length for voice messages. Goodbye.
And so the CLT panels consist of odd layers, usually 3 to 7, with the outer layers going in the strong axis and the inner layers going in the weak axis. Glulam is a stress-rated engineering wood panel, consists of wood laminations or lam that are bonded together to make a durable moisture-resistant adhesives. And these glulam were used for the columns, and the CLT was used for the slabs. Mass timber is popular because it is a sustainable alternative to steel and concrete. For this project, the total potential carbon benefit equated to 511 cars off the road for a year, or energy to operate a home for 222 years. Here's the design team. I won't go into each player, but what I want to highlight is to get the trades and GC involved early, and I'll get more into detail about that later. So here's a brief timeline of the project. What I want to highlight here is between December 2014, when the design team was selected, to October 2015. This 10 months was the full design phase, so it was very quick. The client had a very quick timeline of design and construction because they wanted it open for 2017 fall. So once the design was done, construction started in October 2015, and the superstructure portion was done less than a year later, ready to be open less than 2 years from when design was completed. And I want to highlight the design phase includes a site-specific regulation or code compliance that we had to get around, which I will get into later. This was possible due to external funding in Canada, mainly through the Natural Resources Canada. And this was because there was a strong interest in promoting wood industry in Canada, not just for sustainability, but to build tall buildings. And Canada wanted to be at the forefront in tall wood structures in the world. And then following this, more funding followed in both US and Canada. Now I'll get into more design context for the project. So it's located on the peninsula just outside of Vancouver. You can see Vancouver in the distance here. This is the campus of University of British Columbia. And you can see right here is where the project is. It's kind of on a hill close to the ocean, so you'll get wind loads from escarpment, and that produces very high wind loads. It's also close to the Cascadia subduction zone, so it's high seismic zone here. In Canada, this is the second highest seismic zone after Victoria. And being part of the Pacific Northwest, there's a ton of rain. Now, this might not impact steel and concrete as much, but since timber is an anisotropic material that absorbs moisture, this lots of rain can really affect timber's mechanical properties and its aesthetic properties. So the university had a building that they liked, another student housing on campus that they made out of concrete, and the price that cost was $192 per square foot. So they came to our design team and said, we want a student housing made of timber using this cost, $192 per square foot. So from day one, this was really a driver to keep the cost at $192 per square foot. These are the building codes that were in use at the time. On the left, the British Columbia Building Code 2012. Our design team knew we were outside the design code because this limited mass timber to 6 stories. On the right was the CSA 086 from Engineering Design Wood, which had no height restrictions for mass timber buildings. And our design team knew that we were good in that regard. But I will go into detail later about how we went with the site-specific code regulation. For a unique and new project like this at the time, you had to find alternate ways to procure and go about the project. So not design, bid, build, but rather design assist. So it was very important to bring in suppliers and installers and the GC during the design phase to get design assist real-time feedback. British Columbia has a strong forestry industry with lots of supply, but at the time it was mostly looking like this, these dimensional lumber mills. So at the time, there weren't many fabricators or producers for mass timber in British Columbia. And when considering suppliers, we needed to think about production capacity. Do these shops have enough output capacity to produce the volume of wood? Do they have the species that the design team is looking for? Do the panel dimensions fit the requirements of the project? So as a starting point, this is a rule of thumb that we use at FASTNEP for mass timber buildings. This is for post and plank, so beam and column and slab. 0.25 meter cubed of wood per meter square of floor. Multiply that by the total area of the building, and the estimate was about 3,640 cubic meters of mass timber for this project. The other thing to consider is the supplier's capability. Are they capable of producing a high quality product on schedule? And how long will it take for them to produce it? Today, many mass timber manufacturers are backed up for 6 to 8 months. You need to reserve your place in line, similar to a steel mill order. And since the design team knew CLT was a critical path and needed the suppliers to deliver. Now on to design approach. So keeping it simple, this was overarching design approach for both this project and what we do at FASTNEP. This was especially the case on this project because of the limited budget and the accelerated design and construction timeline. The design team didn't want to be purists and not force timber if it didn't make sense both for cost and timeline of design and construction. Our design team wanted a flow and repetition of structural elements to facilitate fast construction. And our design team was already being innovative with this being the largest application of point supported CLT, so didn't want to be too innovative beyond that. So with any design, you start in concept and you have multiple options. So these were all the options that were explored early on, with 3 of them investigated in much more detail: 2 post and beam options and 1 flat plate point supported option. These 3 went through preliminary costing and discussion and decided on the point supported system. Now we'll go into the building overview. So this is the structural model. You can see the steel roof over 17 floors of point supported 5-ply CLT, supported by glulam columns. And this is all transferring on a concrete transfer slab on level 2. And you have standard concrete pad foundations. The lateral system is 2 full height concrete cores designed as ductile reinforced concrete walls. Now, a lot of people ask, if you're making the gravity system mass timber, why not make the lateral system mass timber as well? So in a high seismic zone here, it actually was technically feasible to do a CLT core wall. However, the client didn't have the appetite to invest the resources or time in seeing if this would work. And so we went back to our keeping it simple approach and just kept it concrete core walls. Our design team didn't think we would get approval from the site-specific regulation if it was CLT cores on top of point-supported CLT. Here is a rendering highlighting all the timber elements. As you can see, this is a majority of the building. So this is the architectural layout here. We have 2 quads at the ends, and this is a isolation view of the quad unit. And in between the quad units are multiple studio units. You can see the isolation of a studio unit here. And so working with this layout typically wanted the short distance between columns is the panel width in the demising wall. So you can see here is the CLT panel layout for our project. So the CLT orientation is in the direction of the building. This will take advantage of the max length panel production, which is about 55 feet. Also takes advantage of multi-span across multiple columns, which is better for redundancy, helps with deflection. And as you can see, we try to stagger the panels as this way we don't amplify the reactions on the middle columns. Here's a quick snip of our envelope being installed into these angles that are screwed down to the CLT. This is a detail of our envelope. It's a structural steel stud system with fiberglass bat insulation, wood fiber, laminate panel, and rain screen cladding system. Now I'll get into the key analysis and design challenges that our design team faced. So as I mentioned earlier, due to the height limitations of the BC 2012 limiting it to 6 stories, we were out of code with this. So, however, UBC is a unique single legal entity that allows it to essentially operate as its own small municipality. And so this allowed the design team to go to the British Columbia Safety Standards Branch and create a site-specific regulation, SSR, which is its own document for this specific site and specific project, interpreting the code to make an exemption for this site. So our design team drafted a document called the UBC Tallwood Building Regulation, which ultimately was exempting this project of this BC limit. However, this required an extensive peer review process from structural engineers, from fire safety engineers, from building officials, from timber scientists and construction specialists to determine if this was acceptable. And this was our path to finally get the building permit. And this was all done in that 10-month design period. Now I'll get into the details about the fire aspect of mass timber. A lot of people ask, you're making a building out of mass timber, why not expose it? However, the design team had to go and cover it up, and I'll explain more about this. So in order for our design team to get an approval from the province, our design team thought it would not be possible to push through to have point-supported CLT as an innovative step, but also to have everything fully exposed, especially with the knowledge and research and the codes of fire in mass timber back in 2014. So our design team decided to use drywall for full fire protection, which was a conservative approach to get code compliance approval. Obviously, many years later, and today, the code has caught up and can now design for exposed wood. And this project was a big catalyst for that. I'll do a little quick side note about how to design for exposed mass timber. It's through an established method called charring, where mass timber elements burn at a predictable rate of 1.5 inches per hour and creates this gray char layer around the unburned portion of the wood. And so you design an exposed wood element of the reduced charge section for the fire hourly rating of the building. Our design team obviously didn't do this, as I mentioned before. If you do it this way, you need to pay more for the columns for the increased thickness to account for this reduced chard dimension. So this is what our design team did, wrapped the columns with 3 layers of type X gypsum. The benefit of this was that it allowed smaller section sizes for the columns and the use of non-visual grade wood since it would be covered up. Here's the typical floor assembly of the project. Starting from top down, we have floor finish, we have the concrete topping. This concrete topping was more as an acoustic layer, and today it can be used as a fire separation layer as well. Below that, we have our 5-ply CLT. We have our moisture resistant partition, GWX partition type X board, followed by a hat track, and then 2 more layers of that fireproofing GWB type X. And that's for, yeah, the 2-hour fire rating. Now I'll get into the details of the point supported CLT system. So this is essentially the gravity system, 5-ply CLT spruce panels on glue lam columns coming from Structural Lam in British Columbia. As I mentioned, this was the largest application of point supported CLT at the time, and it's very efficient, similar to concrete flat plate because there are no beams, thus no horizontal obstructions to MEP. This keeps the floor to floor thin and saves on envelope sizes. And similar to point supported, or similar to concrete flat plate, CLT can span 2 ways in here. So in the long direction, this is the strong axis direction of the CLT, and then the short direction is weak axis spanning with this transverse layers. So it's very analogous to concrete flat plate, as I mentioned. A key design aspect of concrete flat plate is punching shear, as many people know. And so similar to punching shear in point supported CLT, it's governed by this phenomena called rolling shear. So this is where basically the wood lamellas try to roll over each other in this event. So imagine a group of straws, a stack of straws that you have on top of each other, and as you try to shear them across each other, the straws in the back will try to roll over the straws in front of it. So this is really what controlled design. The current design code at the time specified rolling shear capacities for CLT to be 1/3 of the longitudinal shear capacity. So we used hand calculations and used this software called Lubal RFM software. This software has this add-on called RF Laminate, and we use this because it allows you to input and analyze CLT, and you can input the specific layers and its properties, and it even has layers and CLT products from many of the manufacturers worldwide. However, because this was the largest application of point-supported CLT, our design team wanted not just software analysis and hand calculations to validate design, but do our own research as well. This is a simple hand check procedure that we did. So without getting into too much detail, it's based on first principles to calculate rolling shear stresses on the perimeter of the columns. And this was checked against the code prescribed rolling shear stress of 0.5 MPa for this CLT panel, which is about 75 PSI. Again, this is 1/3 of the longitudinal shear stress capacity. However, our design team also wanted to do full-scale testing to verify our assumptions. So 18 panels were tested from 3 prospective suppliers, tested at FP Innovations Lab in Vancouver, British Columbia. And through this test, rolling shear capacities were in fact higher than those published in the code. And our team and a lot of other follow-up research has dove into this more, which I will go into later. This is an example of the failure of rolling shear. You can see these lamellas trying to roll over each other here. And yeah, once you remove the material safety factors along with the LRFD factors, typically see about 2 times the calculated capacity, but in these tests, we saw closer to 3 times the capacity. And so after these tests, our design team had a better understanding of how point support CLT works, and the physical testing was a huge validation that gave our team and the code compliance group more comfort. Another major part of the gravity design was the column-to-column connection. So wanted a direct load transfer from the column above down to the column below, while also giving enough bearing area for the CLT on that floor to rest on the column below. So essentially we have a plate connected to column above that's connected to a small tube that slots into a mirror connection below, but of a bigger tube as it slots right in and locks in place. And then the CLT will rest on the bottom plate and will be bolted to the rods, these threaded rods. And another thing about these epoxied and threaded rods was that it was there to prevent progressive collapse. So say if this column got knocked out, this slab can hang from the column above. This is the column-to-column in action, connection in action. You can see here the top of the column-to-column connection with CLT resting on it, and these are the bottom of these column-to-column connections ready to come in and lock in place and get connected. This type of connection also avoided any force through the CLT, which would have crushed the CLT slab. So this is what the 3D rendering looks like. The main thing is that it was fully enclosed for fireproofing. So with any tall building, we need to deal with axial column shortening. But for our case, we have 2 different materials, the concrete core and the timber columns, and the differential settling from those 2 materials. So Delta 1 here is the concrete core axial shortening from shrinkage, elastic shortening, and creep. Delta 2 is the timber column axial shortening from shrinkage, elastic shortening, creep, and joint settlement. Obviously, these are at different rates because of different materials. The concrete core was constructed before timber even started, and so it allowed a lot of these Delta 1 to occur even before timber columns were erected. So the design team didn't need to account for Delta 1 in this calculation. And so overall, the axial column shortening of these timber columns was estimated to be about 48 millimeters or 2 inches at the top, at the roof. And so the design team had to decide how to mitigate this, how much to mitigate, and where to do it. So this is an example of the solution here. Basically, it's a series of shims installed at the top of the column-to-column connection. This was installed at a higher than the theoretical design datum and higher than the CLT to concrete connection elevation, so that at some time later, it will all even out. And with this, the mechanical had to be flexible, had to use flexible polyethylene piping instead of copper because that's more durable and flexible. This is a photo of the shims in action here. As I mentioned, they didn't want to overcompensate the settlement, so they only, due to many uncertainty factors, and this being the first biggest application of tall timber and CLT, so they only shimmed for about 50% of the calculated settlement to avoid overcompensation. I'll go into the lateral design now. These are the concrete cores that you would expect in many residential towers, especially in Vancouver. Here are some of the lateral design properties. These are ductile coupled reinforced shear walls, and using a large R value was able to reduce the lateral load. The big thing was how to get the diaphragm load from the CLT plates into the concrete cores. And as expected with this building, since it's made of CLT, it's much lighter than the equivalent concrete building, so the seismic forces were much less. This led to savings in concrete core sizes and foundations and lateral elements. As with any project in high seismic zone, you want to do it by capacity design, which is what we did here. So you choose your yielding mechanism, which is the concrete base of the concrete core, and design for this to yield first, and nothing else will yield before that. So you design the other elements, the diaphragms, to the capacity of the yielding concrete core. As expected, this led to congested reinforcing in the core walls and detailed using the special reinforcing criteria per the codes. And the closer the design is to the loads, the more efficient you can make the diaphragm. So this is a typical detail of our plywood spline connecting between two CLT for diaphragm transfer. And so basically it's a top side of the CLT panels indented on both sides, so you can put in a flush plywood spline and screw them in. This is what it looks like in action. You can see the larger nails at larger spacing is for connection fit up, and the smaller nails are for diaphragm shear transfer. And these nails were chosen, rotoblast anchor nails, because you could use a pneumatic nail gun to screw them in, and that would speed up construction significantly. As you'd expect, there are large diaphragm forces that need to get into the concrete core. So use a series of drag straps here, which are essentially steel plates screwed down to the CLT and connected, either welded or bolted to an embed in the concrete core wall. And then along the perimeter of the CLT diaphragm to transfer the diaphragm cord tension across the panels, we used, similar to drag straps, these steel plates screwed down on either side of the CLT joint. As with any tall building, wind can produce dynamic wind accelerations and these vibrations might cause uncomfortableness for occupants on the top floors. So we had to figure out a damping value to use. However, since this was a new tall building made of wood, there wasn't many research or precedents on this. And so I think FP Innovations was doing research at the time and suggested to use 1.5% damping for this. So in this project, prefabrication was a big component of the success. And this was the benefit of having the GC and timber supplier and multiple trades on board during design assist. I know this is pretty common nowadays, but this was pretty new at the time in 2014-15, where the design team included a virtual design and construction modeler, which was CAD makers. And they basically made a full 3D model, including all the trades. This was to assist in design development, decision-making, clash detection, coordination among disciplines, and even did construction sequencing. So you can see this is an example of the trucks coming on site, showing the timeline of them coming on site and bringing material onto the project. This is especially important because there was not much space on site for storage. So this was part of the VDC modeler's tasks. Clash detection, a lot of this happens in either late CD or CA, but the goal of this, because of the really tight construction timeline, was to get this done all in design ahead of time so that prevent any headache and hiccups in construction. And this was also done so these models went straight to structural LAM, and they could start producing high quality, precise panels with the right openings in the right locations. And this was allowing also the tight tolerances that our design team was achieving, 1 millimeter for the timber elements and 0.5 millimeter for the steel. Now I'll go into the construction portion of the project. So did a full 2-scale mock-up of the building. And this was to test out many connections, many interfaces. And this was very successful in testing out the construction sequencing, the fit up, the constructability, and also testing different types of connections. So you can see here, there were 3 different types of column-to-column connections. There's the steel one steel one, and 2 wood steel to or wood column-to-column connections. And based on the feedback from the construction team, decided that the steel one was the easiest to construct. Through this, there were many lessons learned and able to validate design and update details to make the final set of construction documents. Different facades were tested, and so we have precast sandwich panels, we have wood studs with metal panel, and steel studs with metal panel. And this latter one was the chosen. So in terms of sequencing, the entire concrete was poured and done during the winter wetter months. And this was to facilitate only the use of one crane that was allowed on site because of the tight space on site. And this allowed, while the concrete was being constructed, for the timber to be fabricated in the shop. And then this allowed, the idea of this was that the timber would be constructed during the summer drier months to avoid any moisture impacting from rain impacting and delaying the schedule. This provided a 16-week window for the construction team to assemble. This is a typical level of the building superstructure, and I will go step by step of how each individual element was installed. So start with columns on site. You lift them in place into the column-to-column connection below, followed by temporary horizontal spreader braces and diagonal bracing to keep the columns from rotating and tilting. Once all the columns are plumb, stabilized, and in correct location, the CLT gets lifted and fit up into place, connected to the dowels, bolted down at the corners at the column connections. Soon after, someone behind comes and installs all the splines between the CLT panels, along with the drag straps, and connecting the steel drag strap into the concrete core. Temporary railing gets installed, and also the perimeter facade connection angle to CLT so that the facade could connect right here and hang below. So anywhere between 1 to 3 floors behind, I think they started, this is about 3 floors behind, but they were able to catch up the facade installation to only 1 floor behind once they got the hang of it. But facade would get lifted into place and connected to these perimeter steel angles hanging from the CLT slab above. Soon after, you protect the splines and the slab to prep it for a concrete topping pour. Once that's prepped and that floor is enclosed by the facade, you pour the concrete. But before you pour the concrete, you want to moisture test the CLT and ensure it's below the criteria. Otherwise, if it's above the criteria, the CLT can trap, the concrete can trap that moisture in that CLT, and it'll be very difficult to get it out. So it's very important to ensure that the CLT is at the right moisture content before it's enclosed and poured, or the concrete is poured. Once the concrete is poured, fireproof gypsum type X board can be installed, followed by mechanical fit out, and interior fit out can proceed. So here's a quick time lapse of the building. I don't think I'll go through the whole thing, but all in all, this timber portion of the project went very smooth. Obviously, the beginning floors took a bit to get used to, but we think the mock-up really helped in getting the construction in order and fast from the beginning. So the construction team was able to do this within 16-week period. They actually did it in 9 weeks, 44 working days. So essentially 2 months ahead of schedule. This really showcases the speed of mass timber construction. If I can skip a little. But yeah, it went up very quickly. And you can see the facade catching up over time to the CLT. Wrap up with a conclusion here. So if you remember my first slide, or one of the first slides in procurement, we were expecting about 3,600 meters cubed of wood. This was based on the post and plank rule of thumb volume that we had per square meter measurement, and achieved a much less wood volume. And this is because we were point supported without any beams. The cost of the project, remember, our design team was aiming for $192 per square foot. It went up to $232. If you include inflation, this was about a 7% premium. Timber install went up fast, and that was a huge success. Expected the drier months in the summer to rain a little. It rained a lot. So that's why it's very key to construct quickly and cover up the CLT to protect it from the moisture. And our design team was able to achieve the high tolerances that we were aiming for. So some lessons learned from here. Point supported CLT is an efficient system for student residences, micro apartments, or hotels. However, in today's CLT markets with more suppliers and more production, wider panels are possible, which allows for more flexibility in unit layout and thus becoming more efficient for other residential apartment buildings. Keeping things simple really paid off, especially when we were trying to be innovative. We didn't mean we had to sacrifice based on innovation. While we were conservative in some approaches, it allowed the design team to go forward with this 5-ply point supported CLT. And this was especially important when introducing this new this new engineering technique system to get it past the code compliance officials. It was very successful and to involve the trades early, especially for mass timber, so that the supplier can get involved in your design phases and can help with connection or with construction input. The 3D coordination really paid off, coordination of trades. This really prevented any large hiccups on site in CA, since all of this was done in the design. And that full-scale mock-up was really successful as well in testing out connections and testing out construction and fine-tuning the design. And with mass timber, the kit of parts prefabrication has its advantages, using a repeated puzzle-like system that can be easily and quickly assembled on site. So now I'll do a few minutes in our concept lab, which is our internal research and development arm at FASTNEP. So as a company, we try to be innovative and at the forefront of structural engineering, especially with mass timber. We want to push boundaries of code since there isn't as much code about mass timber. And in the past, when we test with universities or with organizations such as FP Innovations for Brock Commons, there's usually long wait times, it's expensive and difficult to get an answer. So our company decided, why not we just create our own testing and research space in our home office, since we like it so much anyway. This is our home office in Vancouver. Top floors are the office space, and this highlighted portion is the concept lab. So I'll just flip through some of the only few of the many testing that we've done. This is testing, different types of wood geometry and members by stacking weights. Test different connections, glued in rod testing by hanging weights. Check composite members, such as this CLT glulam double T, connected between two to create a composite member, similar to try to analyze like a concrete T-beam. CLT shear wall testing and its connection to the base structure below. And then obviously I want to highlight this. So since UBC Brock Commons, we did a lot of point supported CLT testing on our own. This is very loud. Sorry, one sec. And so this UBC Tallwood point supported CLT gained traction among not just us, but multiple researchers. Our company has done a lot of papers and presentations on this. And since then, further research suggests that the size of openings and size of column, its shape, relative stiffness between the CLT and the column, all these play a factor in calculating the force and the capacity in point supported CLT. So we have ongoing research right now. It's still not finished, and our goal is to get it in the building codes. And with our ongoing research, we're still evolving from there and applying it to current and future point supported CLT projects, such as BCIT tall timber student housing in Burnaby, British Columbia. This is again timber student housing. Similar system, 5-ply CLT point supported, however, on steel columns, and the lateral system is steel braced concrete or steel braced cores. You can see it's a little different geometry, all on a concrete podium. Also on some apartments in San Jose, California. Again, this is CLT, point supported CLT on glulam columns. Lateral system is steel cores, all on the concrete podium. And I'm currently working on a point supported CLT project outside DC and Maryland. And hopefully there'll be more popping up in the East Coast. Thank you for your time. And anyone have any questions?
Thank you, Eric. We'll give everyone a few minutes here to possibly chime in and ask some questions or paste them in the chat. One of my first questions was going to be, you talked a lot about obviously buildings in Canada, and I think you kind of touched on it, that technology is trying to make its way into the US. I know I've seen a number of timber structures, but not to this height. I guess what's the tallest that's kind of been constructed or is planned to be constructed in the US?
So I think the IBC just allowed type 4 to type 4A and B, which is up to 18 stories, to be made of mass timber. And so there's now, since that, there's been more of a push from developers and architects to try to achieve that height, which is that project that I'm working on in Maryland is, I think it's about 16 stories high. So that's the tallest you can go by code in the States, at least. And I think it's the same in Canada. I know like the Ascent in Milwaukee that was done by Thornton Tomasetti, that is 25 stories tall and a little taller. And I know they did similar to UBC Brock Commons, where they did a site-specific regulation kind of code compliance path to achieve those heights that are beyond the code specified heights.
Got it. Thanks.
I'll start from the top of these questions. So how early was the full-scale mock-up performed in the 10-month design phase? I believe this was done about halfway or like 3/4 of the way. Obviously, most of the design had to be done in understanding, the thicknesses, the spans, and especially developing the connections and the different types of connections to test. I think it allowed probably like 1 month before the final input from the contractor to like finalize the design from there. But yeah, that was a big push to get that done within that 10-month design phase. Next question was not familiar with CLT. So is there a risk of damage from exposure to water? So yeah, so timber, unlike concrete and steel, is very susceptible to moisture damage. And so it's very important to keep the moisture content of timber below a certain number, or else it starts to lose its mechanical properties, and it's yeah, it really inhibits the properties of the CLT and any mass timber. So many products that we do, we have a moisture mitigation plan to try and let the guide the contractor to do whatever we can and whatever we suggest to avoid mass timber elements absorbing moisture from rain events, from any like spills or leakage or anything. And we have that on every project.
Eric, I'm not seeing the questions for some reason on my end in the chat.
Oh, really?
Yeah.
I see them in the chat.
But you can go ahead and keep reading them. That's fine.
Okay. All right. So next question was, are tall timber structures on concrete podiums? Yeah. So these tall timber are a lot of times the IBC allows basically 18 floors above a concrete podium, and the podium is part of the type 4 building criteria. And it's usually concrete podiums because it's easy to transfer. I'll try to go, let me see if I'll show. So you can see, I think this is a better, usually the grid spacing for the floors above the residential is tighter than the grid spacing that's required for parking per se, because usually the bottom floors of these are parking, not always, I guess for residential, but not necessarily student housing, but it needs to transition to foundation anyway, so make the podium concrete. And that's why then we have a concrete podium with a transfer floor, usually to transfer out the tighter spacing of columns into wider spacing of columns in the concrete podium. Were the column shims on specific floors? Yes. So for this project, it was only on, I believe, 7, 9, and 11. I honestly can't remember why they decided those specific floors, but in all of our projects now, we provide them on every floor. You know, less shims on every floor. It was just over time that system didn't work as well as we wanted it to. And so we used it on every floor, and that is a much better system. Next question I see here. Was wind effect an issue at all being on a peninsula with a significant? Yes. So let me go back there. But this was a light building. So the first few modes had a very low frequency. Let's see that slide. Yeah, so the first few modes had low frequency, so it was very susceptible to accelerations at the top. And so designed to 1.5% of gravity acceleration at the top. And they had to do, you know, their own dynamic wind acceleration models for this specific analysis. Next question, what kinds of program were used for analysis? So for the lateral was ETABS, and for the gravity was this software that I went through real quick called this one. It's RFEM. And this one, we use this solely for CLT and mass timber because it has a lot of mass timber functionality built into it. This specific one, there's an add-on called RF Laminate, which you can create your own custom CLT layups. So you can, you know, input your layers, your longitudinal layers, your transverse layers, input all the mechanical properties if it's a custom layup, or it even has a lot of the layups from manufacturers built in. So you say, I want to use a structure lamb CLT layup. It has that in its database, and you can analyze it with that. Next question. What type of owner approvals and or other validations are typically required for types of timber connections that are not typical conventional? And other So I think the main thing for this, I don't know if the site-specific regulators were as worried about the specific connections and what type of they are. I think they were more worried about, is it going to be safe in a fire event? So in this case, that's why I put in this slide here where these connections still had to be fully covered and fireproofed to prevent any chance of fire damage to the connections. I think I answered all the questions in the chat. If anyone else has any questions, I think we're also close to time anyway.
Yeah, I think that's perfect timing. So I will just share my screen real quick. So big thank you to Eric. Great presentation. Thank you everyone for attending. Like I said, this is our last meeting of the 2023-24 season. So I don't have any upcoming events specifically to list, but just stay tuned for September meeting. That will be our next meeting. So everyone can take the summer off. So thanks everyone again for joining, and thank you, Eric. Everyone have a great
everyone. Thank
weekend.
you, Nikki.